All right, so what they talked about in the video, or what I talked about in the video, I should say, is the idea of reduced row echelon form. So just to remind what we mean by this, because this idea of reduced row echelon form is going to be a concept that we're going to have over and over and over and over and over and over and over again throughout the entire course of the semester. So for a matrix, we need to make sure that all rows of zeros, I don't think I have these in the same order as they were in the video, but that's okay. All rows of zeros are at the bottom of the matrix. So this is row echelon form of a matrix. I didn't write matrix down, but every row of zeros that you have a complete row of zeros at the bottom, or excuse me, a complete row of zeros, they need to be at the bottom. Okay? The second one is the first non-zero entry of any row is a 1. And again, as I mentioned in the video, this 1 is called a leading one or a pivot. I will typically refer to it as a pivot because pivot only has 2 syllables and leading one has 3. Okay. So, the Stickles law of conservation of syllables. Okay? So I will say pivot rather than leading one typically. But as I think I mentioned in the video going through some examples, one of the reasons why we want this as a leading one is the same idea as what you think about when you solve equations. I want variable equals number at the end, right? So that leading one is the idea of a single occurrence of that variable. So I see variable equals something. Okay? And then the third idea is that as you go, I want to write it this way. I'm going to write it in more layman's terms than what I had in the video. So the video said that if I is less than j, then the one that's in row I is to the left of the one that's in row j, right? But mainly, all you're doing is, as I look at the matrix, as I go down, the ones go to the right. You steer a step down to the right, all right? So just to write that down, as you go down the rows of the matrix, the leading ones, or the pivots, go to the right. I can spell. And I'm going to write down an example of something that's in reduced row echelon form and one that's not. And then the fourth thing that we need is with these pivots. Let me write it this way. In a column with a pivot, all the other entries in the column are zeros. Wow. So these are the 4 characteristics of a matrix being in reduced row echelon form. Right now, our idea for matrices, we haven't even done any arithmetic with matrices. That's coming up in the next section, I believe. But our ideas for matrices are simply just a way to keep track of the coefficients when you're solving a system of linear equations. We did that at the end of class last time, right? That really, when you're solving a system of linear equations by elimination, all you really are doing is keeping track of the coefficients on the variables as you go through, right? The variables don't change, right? Because since it's linear equations, you know all of the variables are to the first power. So you don't have to do square rooting of things to change powers if it was a squared, or do inverse sine of things if there was a sign in there, right? the variables themselves don't change. The only things that are changing are the constants, right? So all we've been using the matrices for so far is just basically a table to keep track of how the coefficients are changing from step to step. So every time we have one of these augmented matrices, they always correspond to a system of linear equations. Now again, as we go farther with class, we're going to tie things back to systems of linear equations again, but the idea behind matrices is they're going to have other applications as well, besides what we're doing. But right now, that's all we care about. So with this reduced row echelon form idea, what we're really trying to do is get to a point where we get our variables that we can possibly get eliminated, and be able to read off the solutions. That's the whole idea. So if I write down an example, let's say I had this matrix. Let's say we just had 1, 0, 3, and I'm going to make it augmented. So a -1 and 0, 1, -2, 5. The only reason why I'm making this an augmented matrix right now is because I really want to emphasize this, tying the augmented matrix to a system of linear equations. So the first thing I ask is this a reduced row echelon form? Does it satisfy all of the characteristics? Are all the rows of zeros at the bottom? Well, yeah, there aren't any, right? So yes, by default, we say that's vacuously true. All rows of zeros at the bottom, because there are 0 rows of zeros, so they're all at the bottom, right? Is the first entry in each row a 1? The first non-zero entry in each row. Good, okay. So let's see this one and this one. All right. Is this pivot to the left of that pivot? Yeah. Yeah, good. When I look at this pivot, is everything above and below it a 0? Yeah. Look at this pivot, is everything above and below it a 0? Yeah. Yeah. So I satisfy all of them, right? So this is in reduced row echelon form. I don't need to worry about that, well, either of those other two columns, because there's not another row to get a pivot in, right? We ran out of rows, right? So even though there's not a 1 in this column or not a 1 in this column, it doesn't violate our reduced row echelon form criterion, because my first non-zero entry is a 1. There's not another row here to get me a 1 here to make those zeros. Okay. So we're good as far as reduced row echelon form goes. All right, let's tie this back to systems of linear equations. If these 3 columns represent, say, x1, x2, and x3, what would the system of linear equations be that corresponds to this augmented matrix? Yeah.
Would be x1 plus x3 is equal to -1, or no, plus 3x3 is equal to -1.
Good.
And then the second one would be x2 minus 2x3 is equal to 5.
Good. Yeah, that's right. Because again, remember the augmented matrix is just keeping track of the coefficients for the system, right? And the reason why I put that vertical bar in there is to represent where the equal signs would go. Right? So we see 1x1, because there's a 1 in the x1 column. There's 0 x2s, because there's a 0 in the x2 column. And I'm just reading across the first row here. 3x3s, because there's a 3 in the x3 column. And then there's a -1 for the constant. And then the same thing for the second one. All right. Notice that at this point, one of the reasons why I wrote this particular example down is we're kind of stuck with being able to solve this system at this point, right? And the reason for this is that I've got 3 variables, but I have 3 unknowns, but I only have 2 equations. Now think about this graphically, for those who've seen some 3-dimensional graphing with planes. Think about it graphically. I've got 2 planes, and I'm looking for where they intersect, essentially, right? That's what a solution to a system of equations is, right? Is an intersection of things, okay? Well, if I take 2 planes that intersect, what kind of a shape do I get? A line. How many points are on a line? Infinitely many. So there's infinitely many solutions to this particular system. Right? All right. So here's how we typically write down the fact that we've got an infinite number of solutions. All right. So thinking back again to why we wanted these to be ones, remember? Our goal is to try to say x1 equals something. So that was why we got a 1 on the x1. x2 equals something. That's why we got a 1 on the x2. I would like to say x3 equals something, but I don't have a 1 there, right? All right. So what we refer to this part here is when we have a pivotless column, we say that x3 is a free variable. There's not a specific number that x3 has to be. Okay? Now notice, once we pick an x3, certainly we know exactly what x1 and x2 have to be, right? You agree? Once I pick an x3, I know what x1 and x2 have to be. But I don't have a 1 in my x3 column, so x3 is not determined, right? It's free. It can be whatever it wants. Now again, if you've seen Calc 3, and I know that's not a prerequisite from the class, but I know several of you have seen Calc 3. If you've seen Calc 3, you've got, well, when you did your equations for lines in Calc 3 in three-dimensional space, you usually had a t as a variable and then talked about what x and y and z are in terms of the t. That's the same idea here. What we're going to do is, since we have this free variable x3, and x3 is free, we can pick it to be whatever we want, we're going to let x3 be t, or whatever letter you want. And t can be any real number. That doesn't look much like a b, does it? T can be any real number that you want, which is representing that x3 can be anything. But once we pick x3, x1 and x2 are determined for us, right? In fact, if I plug in t for x3 up into the second equation, what does x2 have to be? 5 plus 2t, right? And if I do the same thing for x1, what does x1 have to be? Okay, so right, negative 1 minus 3t, and you're fine. Negative 3t minus 1 is exactly the same thing. Just write it this way because I'm going to do one specific thing here in a second. That's okay? Yeah, Megan.
So in order for it to be a free variable, it has to be in both of the equations?
In order for it to be a free variable, it needs to be corresponding to a column that does not have a pivot. Okay. So even if there were a 0, say there were a 0 right here, say this were a 0, x3 would still be a free variable because there's no pivot in the x3 column. So then we would just say that x3 has to be some variable t.
Okay, so does that usually happen with matrices with 2 rows?
And it usually it happens a lot when you have matrices that have few, well, it'll always have to happen. I have to be careful a little bit. Typically, if you have fewer equations than you have unknowns, you're going to have a free variable in there for your solution. Now, it's also possible that you could still get an inconsistent system, meaning you don't have a solution. If you get a 0 equals 6, you know, something that looks like a row of zeros and equals a number on the right-hand side. But you get free variables pop up in what we refer to as underdetermined systems. This is what's referred to as an underdetermined system because there are fewer equations than you have unknowns, so there's no way to get a single solution, a unique solution. You don't have enough information. They can happen other times, but that's a typical time when it does happen. All right. Now, only because we're going to be doing more things later with writing things in vector idea forms. You can split this up into a couple of different pieces. If I think of this as, and I know that we haven't talked about matrices and how to add them together yet, but if I think of x1, x2, x3 as a column of 3 numbers, I can write this as a piece that has no variable attached to it, no parameter attached to it, no t, and a piece that does have a t attached to it. What are the constants here for x1, x2, and x3 that don't have any t attached to them? What's the constant part for x1? -1. And what's the constant part for x2? 5. And what's the constant part for x3? 0. And then what are the coefficients that are attached to the t?
-3, 2, and 1.
Good. Okay, cool. This will, one of the reasons why I wrote the solution in this fashion is for stuff that we're going to do later. But notice that the -150 would correspond to the solution that you would get if t is equal to 0. Right? If I just let t be 0, that's the solution you would get. And you can check if that would work. Back to the original system, that would work. The other part, this part, is the set of solutions that you would get if you changed your constants on the right-hand side to zeros. If you put in 0 for -1 and 0 for 5, this would be the set of solutions that you would get for that particular system. I know that doesn't tell you a lot of doesn't tell you a lot about why I did that. We will talk more about that later, but I want to get a little bit used to seeing the solutions in this form. If you're taking differential equations or will take differential equations, you will see solutions in this form as well later on. Maybe not necessarily written as vectors, but you will see things as some typical solutions that you'll see in differential equations are a function without a parameter plus, or with an arbitrary constant, plus a function that has an arbitrary constant in it. You'll see that idea in differential equations. That's another reason why I wanted to write this down in this particular fashion. But is there any question about where I got these two, I'll call them vectors, column vectors for the time being? Is there any question about where I got those two? Does that make sense where those came from? Okay. Now, it is also possible that you could have a system that has more than one free variable. So maybe you've got something that looks like 1, 0, 0, 3, 0, 0, 0, 1, 0. Let's say -2, 5, 0, 0, 0, 1, and just making things up, 3, 2, -6. First question I'll ask, is this in reduced row echelon form?
Yeah.
Yeah, it is, right? Notice that we have, in this particular case, we have a pivot in every row. The pivot in row 1 is in column 1, the pivot in row 3 is in column 3, the pivot in row 5 is in column 5. But we definitely have a pivot in every row in this case. That means we don't have any rows of zeros at the bottom. This is okay to be a pivotless column. This is okay to be a pivotless column because the only requirement we have for reduced row echelon form, as far as where the pivots occur, is that they have to go down and to the right. Right? And then in a column with pivots, there's zeros everywhere else in that column. So we're good as far as that goes. Bless you. How many free variables do you see in this case? I see 2, right? And in fact, notice that as far as the variables go, these are your constants, so I'm not paying attention to this particular column in this case. But notice that as far as your variables go, the number of pivots plus the number of free variables have to be the number of total variables, right? Because either there's a pivot in the column, or there's not a pivot in the column, right? Okay. As goofy as that sounds, that's a concept that we're going to need later in the semester. Okay? All right. So anyway, if we do this in this case, tell me what the system of equations looks like that corresponds to this augmented matrix. If I use x1 through x5 as the variables, what does it have to look like?
So we have x1 plus 3x2 minus 2x4 is equal to 3.
Okay.
And then we have x3 plus 5x4 is equal to 2. And then we have just x5 is equal to -6.
Cool. Good. We agree with that?
Yes.
Yes. All right. So again, the idea of having this in our reduced row echelon form, again, is to see what the solutions are. We see two free variables, and again, with our free variables, we're going to label them as parameters, as other variables. This is not leaving them as x3 and x5. So ordinarily, and this is just more convention than anything, we have our latest one that's a free variable. We'll call it t, and then we'll go backwards up the alphabet. So then x3 will be s. Yes? Oh, yep. You're right. Thank you. I'm too used to the last one being free. Sorry. Okay. Yes, x2 and x4, thank you. Those are the two free variables. So ordinarily we'll let the x4 be t, that last one be the t, and then the previous one be s, and if there was another one before, you'd have it as r, and just work your way backward up the alphabet. That's more convention than anything. The letters really don't matter. It's the concept that matters, that you understand that it could be anything. Okay. All right, so you should be able then to identify the other three. We know that x5 has to be what? -6. Right? That one for certain has to be -6. Once we have that x4 is t, what does x3 have to be? 2 minus 5t? This is where my handwriting gets out of whack. One's a 5 and one's an s, so I need to make sure that I have them written separately. And then for x1, we need to plug in s for x2 and t for x4, right? So what do you get for x1?
3 minus 3s plus 2t.
Good. Excellent. Cool. Now, much like what we did in the previous example, we can do the same kind of thing here. We can split this up into pieces. Now, in the previous example, we had two pieces. We had a piece that had no t's in it, and a piece that had t's in it, right? How many pieces do you think we'll have here? 3, right? Because I've got no parameter, the s parameter, and the t parameter, right? So if I want to write it in that, I'll say parametric form. So we have x1, x2, x3, x4, x5. Again, we have a piece with no parameter. We've got a piece with an s parameter. We've got a piece with a t parameter. What's the piece that has no parameter? Good. All right, we're basically picking off the constants out of each one, right? So 3, 0, 2, 0, -6. Yeah? Okay. The next piece says to pick off what? Yeah, the coefficients on the s, right? What are your coefficients on the s?
-3, 1.
Okay. And then the last one says pick off the coefficients on the t. What do you get for that one? 85. 1, good. 0. Yep, you're right. Good. Fantastic. Now, one thing that you should notice, and this is, again, I'm trying to give you some foreshadowing to different things we're going to talk about throughout the semester. One thing that I notice is where this one had a 1, basically where we picked off where that free variable is, the other one has a 0. Where this one had a 1, where we put it where that free variable is, this one has a 0. Okay? This is stuff that we're going to talk about later this semester as well. We refer to, one of the reasons why we have, in this case, we have what are referred to as linearly independent solutions. And basically that just means that you can't get one of those vectors, one of those column vectors from the other. Okay. And that's, in this case, it's a characteristic of where there's a 1, there's a 0, and vice versa. That linear independence is a huge deal that we'll talk about later this semester. And you'll actually, if you're taking differential equations, you'll talk about it there too. Okay. All right, questions on either of those two examples? All right. So let's talk about how I've given you matrices that are already in reduced row echelon form. And as you know from the video, the whole goal of Gaussian and Gauss-Jordan elimination is to get matrices into reduced row echelon form, right? That's our whole goal. So let's see if we can solve a system and get to that point. And I also want to show you how we can get some use out of the calculator to help us do this. I'll show you one big shortcut on the calculator that you won't be able to use till later. But yes, Jay.
When we're putting our answers in this form, though, what is this called?
Usually it's called parametric form. All right, so this is, probably don't want to do that. Let's just do 8b, and this is on page 20. So we got 3x1 plus 2x2 minus x3 equals negative 15. 5x1 plus 3x2 plus 2x3 equals 0. 3x1 plus x2 plus 3x3 equals 11. Negative 6x1 minus 4x2 plus 2x3 equals 30. All right, we're going to illustrate here this Gaussian and Gauss-Jordan elimination. And I'm going to start with this particular system. Now, one thing that you should notice about this system, hopefully, is you have more information. You have more information than you probably need. This is just from knowledge that you've had from solving things prior to this class, right? If I have 3 variables that I'm trying to solve for, how much information do you think we typically need to solve for 3 variables? 3 pieces of information, right? Right now we have 4, don't we? So this last piece here, well, at least one of these equations is probably unnecessary, or it's going to cause problems, one of the two. Okay? I don't know which yet because we haven't solved the problem. But it's probably either unnecessary or going to cause issues. Think about what I mean by this. Let's think about if we had, say, 3 lines. Okay, this is 4 planes, but think about if you had 3 lines, right? Well, if I have 2 lines, and I try to put it in the third one, either it was unnecessary because it's ending up going through the same intersection point, right? That would be unnecessary. I can already find this intersection point without the third line, right? Or it causes a problem. It doesn't cross in the same point, right? So usually, not usually, always, Always, if you have more equations than you have unknowns, it either is more information than you need, or it causes a problem. So what does that mean from a matrix standpoint? Okay, so let's think about what this augmented matrix looks like. First row would be 3, 2, negative 1, 15. Second row would be 5, 3, 2, 0. Third row would be 3, 1, 3, 11. Fourth row would be negative 6, negative 4, 2, and 30. Let's think about what I mean by too much information, either unnecessary or causes a problem. Well, remember, we're trying to get to the point where we put this in reduced row echelon form, right? So ideally, we would want pivot, 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 right? To say x1, x2, x3 equals numbers, right? That's ideal case, correct? So if I get pivot, 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 what would happen if I got a pivot here? What would that mean? 0 equals 1. That would be a problem, wouldn't it? That's too much information to cause the problem, correct? So if this is going to have a solution, I don't want to pivot here, which means this row is going to have to be what? All zeros, right? Which means it just didn't give you any additional information anyway, because it's just a row of zeros. There's no information at the end, right? So that's what I mean by either, from the matrix standpoint, that's what I mean by it either causes a problem or is irrelevant. Either we're going to get a pivot here, which is a problem, because that gives you what's referred to as inconsistent. There's no solution. Or you're going to get a row of zeros, so you didn't need it anyway. Okay.
So is it going to always be the last row that's going to be an all zeros row, or is it our job to kind of figure out which row is the problem row or all zero row?
Well, when you put things in reduced row echelon form, you'll always stick the row of zeros at the bottom. So they'll always be at the bottom. Now, and that doesn't necessarily mean it came from the last equation.
That's what I was asking.
Yeah. It could have been that you had to swap it down. Okay. So usually we're not going to worry about which one we threw out anyway, because what we want to get to anyway is to let the calculator or the computer do all the work for you at the beginning, so you just see what the answer is, so that you won't even necessarily know which one swapped down to the bottom. Okay. Now, of course, I want you to understand how we get to that point, so we'll be doing that here in a second. All right. So I don't particularly want to do this one by hand, mainly because I'm going to have to deal with a bunch of fractions, no matter what I try, right? Because remember, when we're doing, trying to get this row reduction done, is what we typically refer to this as row reduction. If we're going to put this in row echelon form, what needs to be up in the upper left-hand corner? A 1, right? To make this a 1, I've got some extra work I need to do. Either I need to divide everything by 3, which is going to give me a fraction here and a fraction here, right? Or I need to figure out some combination of, say, the second row and the first row to give me a 1, right? I could do, I could do 2 times this, or negative 2 times this and add to this, and give me a negative 1 and then swap and make it a 1, if I really, really want to avoid fractions. Don't spend a lot of time trying to do that. So I'm going to show you how to do this on your calculator. And let the calculator keep track of the fractions. Okay? All right, so let me do that real quick here. Let's go over to, I think I have this open already. All right, so here is what the TI-84 Plus looks like, hopefully. All right, so I want to do some matrix operations. So if you look right above the x to the negative 1 key, you see matrix? Okay, so this is where all your matrix commands are. All right, so you should have a list of names, and then if you scroll over, there's a list of math operations. And if you scroll over one more, this is how you edit the matrices. Okay. So the first thing, it doesn't matter which one you pick, as long as you use the same one, obviously, as you're going through the whole problem. So let's just do A. All right, so right now it says that if you've never used matrices before on your calculator, it should come up with A as a 1-by-1 matrix. If you have done matrices on your calculator before, it'll be whatever you last entered into A. Okay, so in this case, we want to type in our augmented matrix. There was 4 rows to our augmented matrix, and then 4 columns. And you should be able to use your arrow key or the enter key to go between those two. Now I'm going to hit enter. It should jump you down to the matrix.
So you have to include
The rows is first and the columns is second. You have to include that first, yeah.
and you're including the numbers.
And you have to include, yeah, you want to include the constants on the end, yep. Okay. So yeah, this first number is number of rows, the second number is number of columns, for our purposes here. And now you should be able to just start typing the matrix in. If you use the enter key as you hit each number, it'll go over across a row and then down as you're typing. Okay. So in this case, we have, what was it, 3, 2, -1. Make sure to use the negative key and not the minus key to put in a negative. -15 and 5, 3, 2, and 0. Actually, I have to retype the 0. 3, 6, -3, and 11. And then -6, -4. What did I type? Oh, geez, I've got a couple of bad numbers in here. I was going to go back and check it, I promise. 3, 1, -3, or 3, 1, 3. What did I do? Man, I got a little off of what I was doing. 3, 1, 3. It should be a positive 3, not a negative. Right? And then, apparently I hit 2 6s on this one. -6, -4, 2, 30. 3, 2, -1, -15, 5, 3, 2, 0, 3, 1, 3, 11, -6, -7. Okay, cool. Good.
Is that 30 instead of 3?
It should be 30, yeah.
Is
It should be 30, yeah. All right. You okay with that? Hopefully. All right, so we've edited the matrix A, so let's quit out of here. And the reason I have to quit out is if I start putting in math in there, it's going to try to put the math in where the entries are. That's why I quit out and went back in. All right, so scroll over. There's lots of different things in here. We're going to do lots of these later. The stuff that we want right now is actually at the bottom. I would have just scrolled up instead of down. It would have been easier. All right. One more. Okay. So, actually, A through F are the ones that we're going to use right now. You can probably see B, A and B are ones that you saw in the video, if you just think about the abbreviations. A is reduced row echelon, A is row echelon form, and B is reduced row echelon form. So you can actually put this in reduced row echelon form immediately without having to do any row operations. Okay. That's nice. In particular, that lets you check your answers right now. Later on, you're just going to use this reduced row echelon form and go from there. Because we'll be interested more in the concepts than we are going to be redoing the arithmetic. But I do expect you to know how to do some of this arithmetic, obviously. But I want you to be able to use the calculator to help with the arithmetic. So look at these C, D, E, and F. Now, in the video, I told you about the 3 elementary row operations, right? What were those 3? You can do a multiple of one row and add to a second row, right? You can multiply a row by a non-zero constant or swap. Look, row swap. multiply a row by a constant, multiply by a row by a constant, and then add. This one is just you just have to add two rows together, and no, I won't have to type in 1 in for this one. And so this is just a special case of that one. So your C, E, and F are your elementary row operations. Okay. All right, so the first thing we said we needed to do is convert the first entry to a 1, right? We've got a 3 in the upper left-hand corner right now. We need it to be a 1. The easiest way to do that for our purposes is just to multiply everything by a third, right? Okay. So what we'll do is we'll select option E. That's multiply a row by a constant. The syntax is that you need to put in the matrix A first. I think this is right, now that I say that. And then put in, I think it's the constant first. It'll tell me it's wrong if it's not. And then the row. It's either that or it's the other way around. I think it's constant first and then the row. By the way it's written, it says multiply and then row, right? We'll see. Yep, it's an error. Of course it is. Okay, let's flip it around. It might actually be I need to put the constant first now that I'm saying this. No. Find out here in a second. Nope, doesn't like that either. Okay, so I lied. The syntax on these, some of these things are goofy. All right, try this. My apologies. This is why I'm going to record some videos and put them on YouTube for this as well, so that you can go back and not have me trial and error this stuff. All right, let's try this. Put the constant in first, because I know this is how it works for the other one. Put the constant in first, then the matrix, and then the row. Hey, that worked. Third time's a charm. Okay, so looking at the syntax again, this is how it works for the other oral operation as well. So the multiply says we're going to put the constant in first, then we have to tell it what matrix that the row we're going to deal with. Okay, so constant, then matrix, then row. Notice that it has decimals in it. If you really want to see it as fractions, you could, if you know how to use your to a fraction button, and if you don't know where that is, if you go to math, and then you say to a fraction, it'll convert those to fractions for you too. So again, why I want to show you this is so you can check your arithmetic as you go through these problems. Okay, as you're doing these row operations yourself. All right, so then to do one more, we're not going to have time to finish this whole problem, but to do the next operation would be I need to do what? How do I make this a 0?
Subtract row 1 from the 5. Well, from the multiple 5. Subtract 5. Multiply row 1 by 5 and subtract it from row 2.
Okay, so I would need to do -5 times row 1 and add it to row 2, right? And that's why we need to think about it to use the calculator, because that's how the calculator is going to work. I need -5 here to add to the 5 to get 0, right? All right, so this syntax. Now, by the way, I want to do that on this matrix, not A anymore, right? Okay, so when I type in this syntax, if I go second matrix, go over to math, and go to option F here, it's right here. We said the constant was -5. The matrix we want to use is the previous answer, right? So do second A and S, which is right above the negative sign, right? Use your previous answer. Which row do you want to multiply the -5 by? Row 1. Which one we want to add it to? Row 2. Now I made it a 0, right? That's okay? Now let's do the next one. What do we want to? How do we want to get rid of the 3? Okay. So let me show you one more thing that you do so you don't have to go back in and go through all these different menus. Right above the enter key, you see where it says entry, right above the enter key? If you do second enter, it'll bring up the previous, what you just typed in, and then you can just go over and change the constants. I want this one to be row 3, and I want this to be, keep scrolling, oops, too far, a -3. And since we have the previous answer in there, it'll work from the previous answer. Again, you can do this by hand. One of the reasons I wanted to show you how to do these is so you can actually check your answers as you're going along. There are so many little arithmetic things that you can do in here, it's easy to make little mistakes. Very, very easy to make little mistakes. So I want to show you how to do this on your calculator so that you can check your answer as you go step by step. It's a little cumbersome, but it's not horrible. It's faster if you're not using your calculator because you can actually type in matrices and other programs that are a little bit faster to type them in. That's okay? All right. So we would finish this problem off and get our solutions, but I'm out of time. So, all right. We'll do more of these next time. Have a good one.